Boom. Okay. Here's the here's a table. I redid the table to make it a little nicer looking. So t values in the first column. And what did I do? I went back and I put in like a 2.1 as the approximate value for 3 times root 2 over 2. And then I just start sticking the root 2.1 values inside because it made it a lot easier to do it that way. Then simplifying the same step all the time because you're going to be doing 3 times root 2 over 2 a long time or numerous times. Anyways, so then you're thinking about, is it a negative or positive all the way through? And then here's your linear approximations and go. How many took the time to graph it? 1, 2.
We
Okay.
all did it together.
Yeah, the 3 of us did it
3,
together.
okay. Okay, sounds good. So I'll let you guys take the time right now to do it. Go for it real quick here. Besides the 3 already did.
And besides the calculator was 3.
Uh-huh.
You can just graph it.
Yeah, graph it because we got all the different points here.
That's like, no.
That's like, no,
Literally
can't do
what
that.
we were supposed to do.
That's-
Yeah, we did it, yeah.
I don't think you're supposed to use a calculator.
It's not that,
And,
it's not
can't
that.
just take a screenshot of Desmos and just like print it.
Nope.
Nope, that was not good.
You actually got to put pen to paper.
Switch my calculator out.
Well, you can get the value.
I need to remember to put your batteries in.
You what?
Need to remember to put your batteries in, just in case.
Oh, yeah, I need to.
Because I can just foresee it dying, like while I'm in the middle of a problem and being like,
The last time I switched batteries was for the PSAT, but it's like, you never know.
yeah,
It
just
could
in
die
case.
at that time,
I'll,
and
I'll
never
save
switch
the
it.
batteries that I take out of it, but I'm putting new ones in.
Sounds good. Go for it. So you're going to make a graph. Let's see. You're thinking about what's the lowest x or highest x you can get. So there's a -3 here. Going through this here, it looks like I get to -6 along the x value. That is so strange. I think all of them are negative. Is that right? So it looks like along the x-axis, the highest I go is 0, and the lowest I go is -6. So we're going to be on either quadrants 1 or 2. The y values, let's see, highest 3.1. There's a 4 here. 4 highest y value, and then going down, it hits negative. So how about -2? So then you're making a graph that goes, let's see, I'll go what? I'll go -5 to +5 along the y-axis, probably. Cool. And then plotting these little points here. So 0, 1, almost -1, 3.1. -3, 4. Cool. All right, and then do that other list right there. And yes, I do want you to do it by hand at first, and then let's do it by calculator. Do you guys remember those dot to dots ones when you like what 3rd grade, 4th grade, right? You're given those dots, then you connect them, and then it's a certain figure. I feel this is the same way right here. Because up in algebra, we just graph lines, right? Y equals mx plus b, but you don't ever actually start graphing points. For a while. Okay, Grant is surprised that it's a circle. That's okay. Surprised by small things in life here. So,
Grant is easily impressed.
So let's go with it here. So it looks like it should be a circle in quadrants 2 and 3, a little bit higher in quadrant 2. And then what I did also is I looked at the little center. What's the center of the circle? Just out of curiosity. -31.
Yeah, I don't know, let me just guess.
I know. And then going back to this right here. Go back to the equation itself.
Oh,
Wait, where?
whoa.
So x is 3 cosine t minus 3. Y is equal to 3 sine t plus 3.
Wait, so can you just look at that and just say that's the center of it? So
Absolutely.
if, like the coefficient does.
What?
What's the radius on the circle?
3,
It has to be like.
because of the multiplication. Ow!
So what if the coefficients are different?
Does it have to be like?
Yeah.
Sure. So this one right here would give you the center of the circle, and this one would give you the radius along, at least along the x-axis or horizontally coming across. Right.
So they're not the same would be an oval. So like,
Absolutely. I think we got the oval last time. Did we get an oval last time?
yeah, the other
Yeah,
one
we
it was
did.
4 cosine t and 2 sine t, which makes sense because
Whoa!
it's 0, the center is 0,
Uh-huh.
and then 2 is 2 up, and then 4 this way.
Yep. So the x-axis or the x value, the furthest it goes away is 4 in both directions, right? Because it could be a 1 or a -1, right? You have that little possibility. For the y values, now you're going up and down. Highest it can go is 2, lowest it can go is -2 away from that little center point. So are we good? So there's our circles. Awesome. Or ovals at that point. We'll see if there's any others, because anybody remember conic sections? What were there in conic sections? There were circles, ellipses,
Hyperbolas.
hyperbolas. That's right, hyperbolas,
Hyperbolas, don't forget eclipses.
and the eclipses, according to some.
Yeah.
Yeah. Okay, so let's jam here. So that's the graphing part. We graphed a circle and we graphed an oval or an ellipse. Okay, so let's jam to. So if that's the case, remember in algebra 2, we actually were in terms of x's and y's, right? Now we're in terms of this little t values. So the question is, how do you go backwards? Okay, is there a way to go back to the original circle formula? Let's see if we can. So let me give you an example from the textbook itself here first, and then we'll jump to ours here. So how about this? Going back to the original set, which is x's and y's, this I think makes sense. You take the x value, you solve it for cosine t, and you don't need to write this down. Just kind of think with me because we'll have an example afterwards. You take the whatever the y value is, you set it equal to a trig function. And the question is this: is there any relationship between cosine and sine? Tough question.
Probably not at all, I think.
Yeah.
Yeah,
They're
not-
probably
none.
completely irrelevant to each other.
Totally irrelevant.
Yeah.
I think I have something called the Pythagorean theorem that says that maybe, just maybe. So there's some kind of relationship in an equation sense between those two trig functions. And if there is, great. How about let's plug it in and let's simplify. And does that look like something we know from algebra 2 right there?
Yep.
Hey, that is a circle. I think it's a circle with 0, 0. Is that right? And we have a radius of 125. That's cool. So it's this setting up for the trig functions here. Hopefully there's a relationship between these trig functions to give you that, and you set it in. We're good. Matthias.
How did you get from x squared over those squared to x squared plus y squared?
Ah, gotcha. Okay, perfect. Good question. So exponent rule says if you have a fraction inside here, you take an exponent, the exponent goes to each of the pieces. It goes to the numerator as well as the denominator. And so then you have 125 squared. Then at this point, same thing here. So you square that, you square that. You don't want to square 125. That's a big number. So then what we do is we multiply through by 125 squared. That just cancels the denominators and leaves that guy on the side.
For some reason, I was thinking like, why would you divide 125? But I was mixed up severely.
That's okay. Okay, let's jam with ours. Eliminate the parametric form T. Let's see if we can plug it into a formula that gives us x's and y's only. That's what we want to do.
That's supposed to say parametric or parameter?
Eliminate the parameter. So parameter T. But we go from parametric equations into rectangular
For some reason I
equations.
heard you wrong.
No, I did say parametric,
Okay,
sorry,
okay.
yeah. Right, and let me set this up for writing. All yours, if you want to stay ahead of me. This one, oh wow. The multipliers in front of cosine and sine are not the same. That's no fun. Now let me rewrite it down here. This, I'm going to divide through by 3, and I have my value. That's cool. I'll leave that there. Divide by 2 this time, and I have this value. And I have, whichever way you go, we write it as in terms of sine squared t plus. And this time we're writing cosine first, because if you guys remember back to conic sections, we always wrote the variable with the x first. That's the only reason there. So I got x over 3 squared, y over 2 squared is equal to 1, and like that. This guy's going to be x squared over, they're different this time. That's no fun. I'm going to write 9. I'm going to write, you can write 2 squared. You can write a 4 here. So talk to me if you guys remember back to algebra 2. If the denominators were not the same, did we keep it like that? Did we still multiply through? What did we do?
Wait, wouldn't it be y squared?
And y squared.
Real quick, I'm confused how you got from cosine squared t plus sine squared t to x over 3 squared.
Oh, absolutely. So this one right here, this gets plugged in for cosine. And then you're still squaring it.
Oh, okay.
And then this is y over 2, gets plugged in for sine, and then you square it. Okay, talk to me, Eclipse. We should have done that, huh? We should have done, yeah, let me write off to the side, because I think it'll fill in the gaps here. So, circle equation. It's x squared plus y squared is equal to r squared, is that right? Circle equation. And then make it more fancy, it was x minus h, and it was y minus k is equal to r squared, where h and k was a center. You guys remember that? Is that coming back in memory? Oh yes. Okay, that was one. Next one was, we can skip parabola for now. The other one was ellipses. Or an ellipse. So you should capitalize ellipse. Okay, that was the oval shape stuff from conic sections here. The equation for it was x squared over a squared. See if this is coming back to you guys. Y squared over b squared is equal to 1. We made it equal to 1. We should do that.
Well, that looks like the equation.
Hey, all right. So if you guys remember back to algebra 2, the way it was kept as a squared to b squared is the centers at 0, 0. Let's say this was actually 3 or 9 right now, right? This was 3 squared, right? And so what we did is we went 3 sideways like this. If this was 2 squared, then we just went up 2 and down 2. That was your ellipse. Do you guys remember that? And then to get it off the center, maybe. Raise your hand if you remember that. Let's do that. Yeah, vaguely. Okay, just vaguely.
I remember looking at it.
I don't remember how it works really.
Okay.
This was when we were like in lockdown, so.
Oh, okay, yes. A lot of things have trauma related.
Yeah.
Okay, so are we okay now here? So let me go through that just real quickly here. There's the example, right? The way you would graph that if you were in algebra 2 and not having COVID. is you would take that, you take this guy is to be the length away from your center. And so you just go 1, 2, 3, and you go both directions. And there's your center pieces. And you go horizontally first, and then you take this little 2 value and you do the vertical change first. And that was it. There's your ellipse. Cool, done. If we want to move it off the center, all we had to do is, I'm running out of space. So, dun, dun, dun. Okay, there it is. Moving off center, all we did is we did this. A squared plus B squared is equal to 1, and that's cool. Then at that point, you can do it anywhere. So you have an ellipse like somewhere in space right here. Here's H comma K, and it made it simple to do those. All right, why do we study ellipses? Is because astronomy, for the most part, our planets go in elliptical orbits, as we think
We're
about
all
it
gonna
now.
be astronomers.
Yes, absolutely.
It's important that we're not
Astrology
flat
is
earthers, so let's just start. I
Um,
think in order to understand this, you have to be well past a flat earther level of intelligence.
Oh, no, I'm not doing this math. I don't think it exists.
That's so funny. Or it could be before. It's a geocentric view of the universe, right? All the math worked out just great too. They did ellipses with little, the equations were with little semicircles inside there. So the equations were complicated, but it still worked. You could still predict where Mars will be anytime. So it was interesting. Okay, one more. Do you guys remember any other one from, did we say it today already? Hyperbolas.
Yeah.
All right, that one, the only difference was,
Yeah, I don't remember what this was.
okay, there's your hyperbolas. All it did is there was a minus instead of a plus. Guys remember those? And so,
And those are like the two lines, the two from.
I doubt too many planets have hyperbolic orbits, but it's always hard.
okay, that was the equation for them. And
My God, it's like a circle and more.
this one,
It's like not like a circle. Yeah, it's like a circle, but.
circle but extra. Okay. This one, depending which one was bigger, A or B, it went like this. You guys remember those?
Oh, no, I remember.
All right.
Oh my God, yeah, that's a basketball.
I do remember seeing this. Yeah,
Mhm.
I don't remember specifics.
Okay.
But I remember.
Yo, the planet.
I guarantee that I
planet's
see
not in
that.
a hyperbolic orbit.
Oh, no.
I can't see.
Like,
Yeah.
you're just.
You can't.
Close and then far away, and then just teleport
At
on
all.
the other
I know.
Should get your prescription checked out.
side.
Okay, we good? So
Wait,
there's
so
your,
then is the center for that one in comma K, but, okay.
that'd be H and K. Now the hyperbolas are kind of funny because the point is actually not part of the graph itself, right? Well, actually, no, all of them are like that, right? Ellipses, they don't have a center point. And then I think you guys did this. Did you guys do this as well? Did you guys do this little line like this?
Yeah.
Right? Yeah, just figure out that line first.
I can't remember why.
And
And
then
I feel
once
like
you-
that kind of confused it more
It's
for me,
because
but
you have
also
the
made more
X.
sense.
And they keep getting closer, but they never touch.
Yeah, I remember asymptotes, but I don't remember why.
Yeah, asymptotes.
I don't remember why.
Oh.
I think normally you did the asymptotes because these are graph, and then you just found this point here, right? And once you
Yeah,
had
and then
those,
plopped it, and then you
then you
did it.
just did it. Yeah.
Yeah.
Okay, coolio. That was an interesting review. Okay, so let's go on to exercise 4 for us. All yours there.
Oh, so that was just it? You just tried it?
That was, yeah, I just kind of reviewed real quick here.
Yeah, did we finish?
Yeah, did we finish that exercise?
Oh, yes, we did, right there. This is it, right here. So with the ellipses, what we do is we don't multiply out. With the ellipses, we keep it and we make it equal to 1. Only time you multiply it out is if the denominators are the same. And that point, because we want to put into standard form for a circle. Good, that's,
So this is relating to what we were doing before, because we were making ellipses. And this is just a, okay.
So if
Good,
the
yeah.
denominators were the same, you could solve it like an ellipse, but it would look like a circle.
yeah, it gets more complicated,
So it
yeah,
doesn't make
because then you have,
sense to do
cool, we're good there?
Mhm.
So standard equation for an ellipse, it will be like that. You want to write as a fraction set equal to 1. Hyperbolas, yes, you set it equal to 1 still. Keep the denominators in the denominator. So all yours for this one. Example 4, give you guys 30-second head start. Have fun.
Oh no, oh no, oh no.
Okay, 30-second head start, finished. Question, is there a relationship between cotangent and cosecant? Ah, bummer. We might need Adrian's book. And all eyes on you. Actually, no, just 4 eyes on you.
Everyone look at Adrian.
Let's see, not the front cover, the back cover. You want to go back
All
cover.
right, that's a
I
start.
was gonna just wait for a little bit longer.
Warmer.
Okay, you're getting warmer.
Alright, we'll just review every single property.
Uh-huh.
I will find it.
You probably want to
Recite the
go
whole
to the
bunch,
next
please.
page. Yep, perfect, yep. Warmer.
Warmer still.
I mean, these are all from chapter 8.
You know, at
That's
that
no
point,
fun.
you can't really get cold.
Yeah, I mean, identity is around the first section, so that we're.
I steered you in the wrong direction. Go ahead.
I'm literally staring at the
This is
identity.
why you
You're wrong.
I mean, 1 plus cotangent squared is cosecant squared. Don't use that.
Cotangent squared.
Yeah, I think that's probably exactly. Like, I was literally staring at that, and then he's like, no, you're on the wrong road. Yes, I'm wrong.
Made you go a little longer around. Thanks, Adrian.
Ow.
Okay, all yours. Finish it off, and then let's see. I think we're gonna have to set equal to 1. I believe. Maybe we'll see. So notice on this one, we're gonna plug in the 1. Cotangent is here, so we're gonna plug in the x over 3. We're gonna square that. We're gonna plug in, let's see, cosecant. This is y minus 3. We're gonna square that. So we have this on our hands. And so the denominators are the same here. The only problem is when you try to make it into a circle equation, let's move, let's
Oh,
see,
no.
which one should we move?
Is this gonna be a hyperbola?
I think so.
Dear God.
Whoa.
Let's see, let's move the y over, the x over to that side. Let's see, I'm gonna move the x over. So how about x squared over 9? It's a minus time. Plus y squared over 9.
Why wouldn't you do it the other way?
Yeah.
Yeah.
Because
So
then
you have
it's-
to-
then it'd be on the
You could do it the other way. Here, which way you want to do it? I'll leave that up there. Which way would you do it, guys?
I would have y squared over a minus x squared over a.
On this side? So x squared over, it's 9. And then that way.
Certainly.
And then we'll move the -1 to that side. We good? Can we do that in our heads?
Wait,
But then to make it a positive one. you have to move it and then-
Yes,
And can
okay.
you not have it y squared over 9 and then minus x
Like,
squared over
would that
9?
mess it up? Yeah.
Yeah, here's the,
Can't you just do x squared?
I'll let it filter here for a little bit, yeah. Bummer, we have that minus in the middle. That's the problem. Okay, so if it was a plus and the one was a plus, it would be a circle equation, everything's fine.
It was gonna be a happy hyperbola.
It's a happy hyperbola. Because that positive one has to be at the end. So to make this to be a positive one, we have this on our hands,
Yeah, okay, that makes sense.
and that is no longer a circle equation.
Wait, so even though it's not the y that's negative, it's still a hyperbola.
Yeah.
Correct, yeah. For circles, both have to be,
So
And-
why couldn't you just do y squared minus x?
Yep, you could. So, eventually the way we write it in algebra 2 is we like the one to be the positive to be in front, the one that's negative to be on the back end, and the one to be positive.
That's what I was saying.
Yeah, that's the problem.
Of the,
So
Figure
the
that
reason
out.
why this is a hyperbola is because of the negative, which is the minus.
If it was a plus, be a circle, multiplied by 9 both sides, and be done.
So can we write it as 9 squared over 9 minus x squared over 9? Or is it just the correct way to write it the way? the first one?
Let's see, this way is fine. There's nothing wrong with that. This way is the more preferred way, because
Okay,
that's
okay.
the way we normally write hyperbolas. We write the one that's negative
Okay.
second.
That's
in
what
the
I
equation.
didn't know.
Whew, okay, are we still getting through stuff? Are we good? Okay, next on the list here. Let's do this here. Yeah, I think we should be able to finish. Let's jam. Don't need to write this stuff down, but let's make our models realistic, and then we'll get to an equation in just a second here. So this little Ferris wheel that we have, let's do this here.
All right.
So-
My arch nemesis, George Ferris. Oh, yeah, right.
Sure, why he's your arch nemesis?
Yeah.
Okay, so we have, we did the 125, we have it on the origin. Oh, you know what? Hold on, that's why. Do. There we go. Finally, I can see my little. Hey, you guys tell me here, is it easier to go with this little cursor thing or the laser pointer? Ooh, how fun is that?
Whoa.
Da-na-na-na-na-na-na.
Oh.
Oh, wow.
Whoa.
That's so
That's
cool.
like, it's almost like a.
It's a little
cursor,
easier to see
but
further away.
Okay.
Infinitely more cool.
Okay, so the equation that we had was, what was the equation we had? Cosine t, right? X is 125 cosine t. And the first equation we ever did in 6.4. X was 125 sine t.
Yeah.
Y was 125. Oh, it's right here. Right here. X is equal to 125 cosine t. Y is 125 sine t. We did this, we graphed it for a whole 2 days. We're good? Okay, so it was a circle at the origin. Now the question is this, you guys talk to me here. How do we get this to be, there's a radius of 125 feet for this. And then we're also going to be 14 feet high off the ground. So what I want is I want an equation that moves this right here 125 feet this way, we're good, along the y-axis, and then compensates for, you know, when you get on the Ferris wheel, you got to put on the stairs, get up the stairs. So there's another 14 feet here.
So you're moving it
Burn the
up
stairs.
125 and then also the
The Ferris
14 or
wheel.
whatever it was?
Yeah, and then moving another 14. So 139. Where should we add in the 139?
Sink it at last in the depths, indeed.
Wait, sorry.
Yeah, I want to.
No longer
Add
14
the
feet,
139, you wouldn't just add the 14 feet?
So I want to move this. So right now, if I'm thinking this is ground level, I have the center of my Ferris wheel on the ground. I don't like that.
Oh,
I
okay.
want to move my Ferris wheel up.
I get it. Okay.
Yeah, it's radius,
I mean,
and then also,
it'd be funny if it was on the ground.
That would be pretty
and
cool.
also the fact that it's still, you have to get 14 feet high to get to the bottom of it.
Right.
So,
I think you want to be able to-
uh-huh. We're trying to move this Ferris wheel, Grant, we're trying to move this Ferris wheel 139 feet high. What do we do?
So would it be y minus 139?
You could bring it to
The
the.
Ferris wheel does not exist, so how are we moving it?
Well, so it's halfway sunk in the ground.
Since it's an
Yeah,
arcade.
but
game,
are
Are
we
you trying to
Here.
figure out how
We
high
just
it
have
is
to
up
move
off the ground? Like, I don't understand.
Sure,
wait,
sure.
so-
Let's back up. Thank you, Georgia. Sure. We are trying to model a Ferris wheel, the height of the Ferris wheel, or the where you would actually be sitting as you're circling around. We're trying to model it better than what we had before.
Wait, so are we trying to get it into a circle equation?
Still, we want to keep it as a circle. We just want to make sure that we have we've thought through the theoretical Ferris wheel to be 125 feet high, and compensate for the fact that it is it's also 14 feet above the ground as it sits. The
Could you
fair.
solve it with 125 and then just bump everything up by 14?
I think we can bump it at the same time. We just need to know which one to bump. Georgia, real quick, I just want to make sure. Georgia, do you understand what we're doing?
So yeah, we're just putting it on the ground in the area that we want.
Uh-huh.
Bump the
Okay.
center
Correct.
point up.
So, yeah, would it be 125 sine t plus 139?
I think so. Everybody okay with that? So in order to affect the vertical change, all we do is we just add whatever we need to y, or we subtract whatever we need for y. So let's move that up. That's cool. That's going to be enough. So as we do this, hey, that's no fun. It doesn't allow me to move. No fun. Oh, it'd be good if it turned on. It'd be great. There it is. Okay, are we good there? 139 feet. We just affected a vertical change. And notice the x is not affected at all. That's the cool thing about parametric equations. I can move this however I want, right? And so then the next thing is, how about if I have a booth that's 200 feet away, and I'm going to make the booth be the origin. Hi. So see if this makes sense. I got my little booth right over here. All I just need to add is 200, right?
Wait, what are you trying to solve for?
Sure. I'm just making this a more realistic Ferris wheel.
We're just moving it around the ground.
Yeah.
Literally.
Essentially
You're
here.
trying to
Drawing it in
move, did you
different-
say you're trying to move the center point to the booth? Is that what you're saying?
Yeah, the booth is not going to be our center point. So the booth is, should be at the origin.
Not on the Ferris.
So, and the Ferris wheel is 200 feet away from the booth to the right. So all we're going to do is just take an extra 200 right here, add it to the x value, and I can move it horizontally any which way I like. Is that, we good? Just like we had that circle that's centered at 3, -1, right? Or -3, 1. And we're just centering.
So you're saying to go up or down, you change the y, and to go side to side, you change the x.
Absolutely.
I
Uh-huh.
think the whole
And they're
Ferris
totally-
wheel thing is complicated.
Complicated? Okay.
If you realized you,
Sorry.
if you realized you wanted to build it 50 years ago, like what would you change to move it back in time?
I'm not even going to go there.
Because y is the second dimension, and then we're going third dimension, but the fourth dimension, that's what we need.
I'll stop there.
Alright.
We're gonna have to grab it.
This is just trick. We're not even the rest of the road, right?
Okay. Are we good there? If we were to graphics,
Yes.
if we were to graph it, it would look eventually like this right here with a little
Yeah, we
trace
don't wanna
button.
move it in space this time.
And so now we have a little circle that is 200 feet away from it. And now we have it positioned the way we want it. So that's kind of the realistic.
Someone really needs to write a short story. This would be a good idea, where someone figures out an equation, like for mathematically an equation to move things back in time or forward in time.
Oh, but they can't apply it to real life. It's
Yeah, it's literally just a theoretical equation.
It's just on paper, you can like move things in its plane.
Well,
I
so
think that's
yeah,
just
they
future.
want to change time, but they can't. So
Yeah.
just keep writing equations.
How they're so upset because mathematically it's supposed to work, but it doesn't.
That's funny. Okay, we're still gonna stop here. I still haven't finished
I
6.4.
mean, if you accelerated the Ferris wheel faster than the speed of light, it might time travel.
Wait, what if you accelerated?
I'm so
What if you
sorry.
time travel by accelerating the Ferris wheel? You're back.
Did you get that?
Before he was born.
I
That's what would happen.
Yeah, you.
Would you never have done that in time because the Ferris wheel was never invented?
Oh my
So, yeah.
God.
The patience you have with this class.
No, just with 3 people.
I think that,
Okay.
I think that
Yeah.
more is the.